Okay, so baseball leaves a bat with an initial speed of 30 meters per second and clears a fence 90.5 meters away. The height of the fence is the same height as the initial height of the batted ball. If the distance traveled is given by d is equal to VO squared times sine of 2 theta over 9.8, where 9.8 is in meters per second squared, find the interval of possible launch angles for the ball. Now that seems like a lot, but if you think about it, we're really not asking for anything that's too complicated here. We're really just saying, hey, what angles can the player hit this ball so that if he hits it, too low, it's not going to go over the fence at all. It's just going to, ground out. But if he, hits it too high, if he hits it on too much of an uppercut, he's going to end up hitting a pop fly. So we don't want either one of those situations. So what we're going to want to do here is to see what angles at which he can hit that ball at that speed so that it's a home run. So let's go ahead and look through this. Well, really all we're doing is we just have to use this formula that they give us here, which tells us that the distance that we hit the ball at is equal to VO squared sine of 2 theta all over 9.8. And really, so what does all this mean? Well, that's the distance that we hit the ball at. VO is actually going to be the initial speed. That's the initial speed at which we hit the ball. And everything else, if you recognize 9.8, that's because that is the force at which gravity pulls to the Earth, right? 9.8 meters per second squared. So that makes some sense why that would be there. So all I got to do is just plug some stuff in. So what we're going to do is we're going to say, okay, well, we know that it is the distance that we have to hit it is 9.5 meters, or 90.5 meters, excuse me. The initial speed is actually up here. It tells us in the problem we hit this with an initial speed of 30 meters per second. So we just plug that in there, 30 squared. Sine of 2 theta on top, and then with a 9.8 in the bottom. So now we multiply both sides by 9.8. And over here on the right, it actually cancels. And then on the left, we're going to want to multiply 9.8 times 90.5. And I'm actually going to move the problem over here so we have a little bit more space. So 9.8 minus 90.5, if you enter that into a calculator, is going to be 886.9 over 9. Okay, so 9.8 times 90.5 is 886.9. 30 squared, so if I take 30 and multiply it twice, well, that's 3 times 3 is 9. And 30, if I'm multiplying 30 by itself twice, that's 2 zeros, so that's 900, with a sine of 2 theta hanging out behind it. And so what I'm going to do here is divide by 900 to get the sine out of the way, or to get the sine by itself, excuse me. You'll notice I already did that here, because in an earlier take I did the dividing by 900 too early, so that kind of saves it. Little editing trick. So here I'm going to put, sine of 2 theta over here, and on the left side I'm left with 886 divided by 0.9 divided by 900. Okay, so now what do I want to do? Again, that's 886. Let me fix that. Okay. So now how do I get rid of sine? Well, of course, to get rid of a sine, I take the arc sine. So I want to take the arc sine of both sides. And the arc sine, as we know, gets rid of the sine. So we get that 2 theta is going to be equal to the arc sine of 886.9 over 900. You need a calculator to do that. So if I think about it, well, that's going to be second sine to get that. It's going to look something like this. But again, it means these two things mean the same thing. And that's going to give us, if I enter that in, again, make sure your calculator is in degree mode. That's going to be 80.21 if I enter that in. Now, here's the thing, though, is that we actually just got the arc sine of 886.9 over 900. And what that gave us, if I kind of draw out a unit circle here, is that gives us the sine, so out here at 80.21, that tells us that the sine, or the y-coordinate, cosine doesn't matter, that's usually the x-coordinate, there is 886.9 over 900, which if you think about it is a little kind of close to 1, right? It's really close to 1, which is why it's way up here. It's almost 201, where sine would be 1, but it's not quite there. So, but the original question is which angle inside of the sine would give us that coordinate, and we got 80.21, but remember, arc sine can't go past 90 degrees. So what we have to do to fix the problem is say, well, there's actually another coordinate over here where sine would be positive that would also have a y-coordinate of 886.9 over 900. So we have to remember that. And the angle there actually would have a reference angle with the x-axis of 80.21 degrees. That's what would happen there. Well, that's nice, but I actually want the angle, so from the axis here, the initial line to the terminal line, I want to know what this angle in blue here is. And how do I get that? Well, I remember that the line is 180 degrees, and all I have to do to get that is subtract the reference angle 80.21 from 180. And so I'm just going to do that really quickly. Again, you could do this in your calculator, and that's going to give me 99.09, which is the other angle that we're going to get for over here. Again, I hope you're watching this video or you're listening, because you can kind of tell what I'm doing here. Okay, so we're going to want to divide. Now, notice that didn't just give us theta, that actually gave us 2 theta, and we want the angle. So we're actually going to want to divide both sides by 2. And because we're dividing both sides by 2, well, again, we said there were 2 solutions here, so we're actually going to want to divide both of them by 2. And I'm going to put that over here. That's going to give us that theta is equal to 82.1 divided by 2, which is 40.105. And 99.09 divided by 2 is 49.594. So what does this answers mean? Well, these are our intervals. These are the angles at which that player can hit that ball and still expect to hit a home run. So that means at 40.105 degrees or 49.594 degrees. So basically what this is saying is that this player has to hit it just above 40 degrees in order for it to go over that fence, but he has to hit it under 49.594 in order to expect to not pop it up too much so that it just kind of pops up into the outfield and doesn't go over the fence. So he has to hit it between those 2 angles there. Okay, so let's go ahead and turn to the next page and look at this problem. So this one says, find the interval of possible launch angles required to clear the fence if the initial speed was increased to 35 meters per second. So all we're doing here is we're going to literally doing the almost exact same problem, except we're just changing one number, which is the initial speed. Now I would highly recommend rewriting the formula from the other page here so that we don't have to keep going back and forth to reference it. And of course that was d is equal to the initial speed squared times sine of 2 theta over 9.8. Okay, so let's fill that in. So we know the distance doesn't change. The distance is still going to be, oops, dropped my pen, 90.5 is equal to, now the initial speed is changing to 35 squared. Sine of 2 theta stays the same, and so does 9.8. And the process pretty much is just the same as it was for the last one. We want to multiply both sides by 9.8, which cancels it down here. 90.5 times 9.8 is literally the same thing we got on the left side earlier, which is 886.99. 35 squared, that's something you can do in your calculator. You actually could use a sum and difference pattern there if any of you are interested. You could do that twice and then use the sum and difference pattern, but you could just use your calculator, that's fine. That's actually going to give us 1,225, and then sine of 2 theta is sticking around for the ride. Okay, so now we just want to divide both sides by 1,225. Cancels. We get that sine of 2 theta is 886.9 over 1,225. Again, at this point we want to get rid of the sine, so we'll take the arc sine of both sides, and we get the arc sine of 889 over 1,225. The arc sine is going to cancel the sine, so we just get 2 theta on the right side. We enter arc sine of 889 over 1,225 into our calculators. That's going to give us a grand total of 46.39. But again, remember, we have to take this angle to get the other sine that would have this as our coordinate. We have to subtract that from 180 degrees. That's going to give us 133.61. Again, feel free to do that in your calculator as well. And then, of course, we want to divide both of these by 2. And from doing that, we get that the thetas have to be 46.39 divided by 2, which is 23.195, and 133.61 divided by 2 is 66.805. And again, what that means is, again, the interval that the baseball player can hit this is 23.195 and 66.805. And again, that makes some sense here, because we'll notice that interval is actually larger than our original interval that we had over here at 40.105 and 49.544. And the reason for that is that if he's hitting it a bit harder, right, if he's hitting it at 35 meters per second than he was hitting it at 30 before, we should expect that interval, the margin of error for him to be able to hit a home run would be a bit larger. Because if he hits it at a lower angle, well, the ball's going to get over the fence faster, so he doesn't need to hit it as high of an angle. But if he pops it up a little more, the force of this faster speed might still get it over the fence. Okay, so now what I'd like you to do is go ahead and try B. Again, notice that the only difference here between the original problem and this is that the distance is going to go to 80 meters. The initial speed remains the same as it did in the first part. So go ahead, stop the video, give that one a shot, and then come back and we'll work it out together. Okay, so I'm assuming you stopped the video and worked through this. So let's go through it together. So now, again, the initial speed from the original problem is going to remain the same, that the distance is going to move to 80 meters. So the difference between the original problem and this one is we're actually going to enter an 80 on the left side instead of 90.5. But everything else stays the same as the original. We square 30. We get sine of 2 theta over 9.8. And again, same story as before. We multiply both sides by 9.8. Those cancel. 9.8 times 80, we actually have to do the calculator since we've never done that. We enter that in, that's 784. 30 squared, we remember that's 900. Sine of 2 theta is hanging around like a creeper. So, divide both sides by 900. Get the sine by itself. 784, we're going to say 784 over 900 is equal to sine of 2 theta. Again, we take the arc sine of both sides, so that's going to give us the arc sine of 784 over 900. Arc sine will undo the sine, so we get 2 theta. And to find 2 theta, again, we just take the arc sine. And when I do that, the one that I get is going to be, I'm going to put it over here so that the numbers go in order. The number I'm going to get from entering that in my calculator, what it's going to spit out is 16.49. But again, what I want to do with this number is subtract 180 from it, or I should say subtract it from 180. And when I do that, that's going to be 119.51. But again, we have 2 theta, so we're going to divide that by 2. Everything by 2. Theta is going to be 60.49 divided by 2, which is 30.245. And 119 divided by 0.5 divided by 2 is 59.755. And again, what that means is now the interval for this baseball to hit this ball is between 30.245 degrees and 59.755 degrees. And again, it makes some sense because this is a much larger angle range than it was our original problem, and of course if you are closer to the fence you don't have to hit it as hard or with just the right degree in order to get it over that fence of 80 meters. So okay, so that's the word problems for today. Go ahead, show that to me so that I know that you took the notes and watched the video for your daily grade, and we'll work some more problems next time. I'll see you guys then.